Now in this one, let's uncover loops. Let's unveil loops. So like you hear the word loops or a loop. A loop simply means repetitive events. Now, in the previous section, if you remember, in the previous section or previous sections, we had, let's say, buttons. Let's add buttons. Let's come here and say, let's have buttons. We can come around and say, let's have buttons. Let's have buttons. Let's have buttons. Okay, button, or let's have push buttons. All right, so let's have a push button, right? Let's have a push button. So now we've added a push button to we've added the push button. Yes, we've added a push button like so. Let me extend this. Now, we've added a push button. So let's first, so when we press, it closes, right? So guys, I changed the environment because this one will be much easier as we progress. It will be much easier and less costly. It will become easy to understand much better than the previous environment I was using to draft the circuits. So, like we are saying, now let's look at loops. Now let's first create a scenario to understand loops. In the previous section, so let me drag this like so. Let me drag it around there. So, okay, around there. So for now, let's have one button connected to PB2 or D2, right? You get the point? So the other end, let's have it connected to ground. I'll copy. So someone said, please show us how you come up with the circuit. So I'm like, all right, I can do that all day long. All right, so now, excuse me. So now we have a button now. We have a button. So now to demonstrate the pull up, to demonstrate what I was talking about previously as the pull up, I'll say resistor. All right, so let's have a resistor. All right, let's have a resistor. Let's rotate. All right, so this resistor can be connected to there. You remember me talking about a pull up, right? On the other side, let it be connected to a voltage source. And this voltage source is 5 volts. So let's set that voltage source to 5 volts DC, fixed voltage, right? That's a fixed voltage. So in this environment, VCC and ground are already connected to VCC, that is our supply voltage, and the ground is connected to ground, and that's 0 volts, right? That's our GND. So by simply now, look at this, without pressing. So if I don't press, right, this push button, now let's start a bit more about hardware. If I do not press this push button, so this point through the 100, so I can even increase this. Let me increase this to 100 kilo ohms. Yes. Now let's make 100K. So 100 kilo ohm, a very big resistor value, right? So it's like it is pulling this GPIO PB2, right, all the way to VCC. That means without pressing the button, this GPIO is at 5 volts. So that is equivalent to coming here and saying, we can come here and say, let's first create let's label PB2 as the button pin, right? Or as the switch pin. Let's call it button pin. So that GPIO is a whole number, so it's an integer, right? We can represent it with an int. Okay, so we can say button underscore pin. I'll talk more about as we progress through the embedded C++. I'll talk about more about variable creation and naming, variable names, right? So button pin, okay, this is assigned to which value? 2. Assigned to that value 2. All right, so what I was explaining, doing this physically is equivalent to coming here and saying pin mode. Remember, we have to declare, we have to set that GPIO as an output. We say now, instead of using the number 2, let's just do this. Copy and paste. If you don't copy it properly, you'll have issues. So pin mode, remember, is a command or a function. Let's call it a function. Let me introduce the term function. It's a function that requires that has two requirements to do its tasks, right? So it requires 2 parameters. So the first one is the GPIO, and then the state in which you want it to be, output or input, and nothing else, right? So in this case, we want this to be input, and capital input. Input, you can say input pull up, input, I think there is an underscore. Let me try to verify. If I have it written in the wrong way, it will flag it. If I have it written in the wrong way, it will flag it. So it has compiled, right? There are no issues. So that is how it's written, input pull up. What input pull up does, so you see, it's a macro, and I will explain what a macro is. So it's a keyword. It's already a predefined keyword. It's already known by the IDE, the Integrated Development Environment. So it's a keyword. It's known very well. So, and we've created a global variable. This now is a global variable. And I'll keep on repeating these terminologies until they make sense, right? Global variable. That's why I can access it anywhere in between the loop, the setup, and the loop without repeating it. So it is global. It's known everywhere. Think of it as an artist. Let's say Chris Brown or any other famous artist, right? Known all over the world. So anywhere you talk about that artist, someone knows that artist. Now that becomes a global artist, an international artist. That's the term we use in that scenario. Now for variables, we have something similar. We have variables that we can access anywhere in the program, and we have ones that we can't access anywhere. We only access them under specific scopes or closed off regions, right? So those are local variables. But ones that are outside of the setup and the loop, we call them global variables. Now we can even create local variables, and we may create local variables in this lecture, right? We may create local variables in this lecture and see how far we can go with that idea. So now this statement is exactly equivalent to doing this physically in the real world, right? And this is preferably, this is what I do in real life. This is what I do. This is what I do in real life. So I don't rely much on this because this is subject to someone forgetting, and the moment you forget it, there is no way of looking at the circuit or the system you've built and say, aha, someone forgot to add a pull-up. And someone will ask a question. Why are we interested in, first of all, having this GPIO pulled up through the 100K to VCC or to 5 volts? So in theory, for those who remember the digital electronics classes, we can have a state. In digital electronics, we have 0 or 1. In theory, that is ideally. But in the real world, real components are susceptible to temperature changes, electromagnetic interference, and very many other things that exist in the real world, right? That we do not base on in the ideal or theoretical world. So you will find that a GPIO does not have a definite state, not until you define it, right? So it can be having a floating voltage. Remember, logic levels have what we call logic levels. So logic level low, let me just write a little bit here. Let me write a little bit down here. Let me write down. So, all right, we have what we call logic levels. We have, these are represented with voltages. So a voltage between 0 and 0.8 volts. So that one represents logic low. And we have voltages between 2 volts to 5 volts. So this represents logic high. But there is no law in physics that stops a GPIO from having, let's say, 0.9 volts. Someone could argue that is not low. Someone could still argue that's not high. So that's not a definite state, right? We have now the unused region. So you get the point. So there is no law that stops our system from having 1 volt. We're still not sure whether that's a high or low. So to make sure we have a high or low, we either pull up a GPIO or pull it down. We will see the pull down part. So it depends on what you're doing, right? So that's very important. Logic levels are very important. So for those who didn't understand your digital electronics very well, at this point, I have nothing much to do for you other than to just make quick recaps for those who didn't understand. All right, so now we have our setup. We have a potentiometer. So it's nothing more than a variable resistor, whereby the more it changes its resistance, the voltage drop between the center point and the ground keeps on shifting as you shift the knob. I remember demonstrating this in the previous lecture, so I don't expect anyone to ask me what a potentiometer is. So we already know what that is for those who watched the previous lecture. So here we are. I think we are set. So on the other side, if I press, that means this GPIO is going to be pulled low. Is going to be pulled low by the switch. It's no longer high. So when I don't press, it's high. It's very important actually to analyze this before you even write the code, right? So when I press, it goes low. So that means us detecting a low on PB2, right, indicates someone has pressed the button. Do we get the point? So I think that brings it out properly. So this is the same as this, though I would strongly advise you to take this. All right, so if we do that in that case, we don't even need to specifically say pull up. We can just do that. Input. Okay. So there is another way. There is another way of doing this. We can come here and say digital, right? Button pin high. What this does, remember we've set it as an input. Now we are writing it as if it's an output. So what it ends up implementing is a pull up. So though I don't advise you to use this. So for now, let's first do away with it. So we want to implement loops. Loops have the following. We have what we call a while loop. We have a while loop. One of the easiest, we have what we call a do while loop, right? So this was the first one. That's the second. right? So I'm adding dots so that it stands out. We have what we call a for loop. Yeah. Each and every one of these can be used to help the program. Remember, control structures are made of ifs, else ifs, switch cases, right? And loops. So when do we loop around? When do we have a repetitive kind of execution? So let's create a scenario. Let's say we have, now let me add an LED. Let me add an LED to the mix as our actuator, right? Because a full embedded system has input, process, and then output. That's the actuator, right? So let's put it around there. Then we have LED. All right. So here is a generic LED, right? Let me have it connected and rotate it around. Rotate. All right, I'll take this back. Okay. So the circuit is getting more involved, right? So I'll connect the longer side to the GPIO. The shorter side comes to ground, right? So you get the point. So that is how it will be. So we can even choose the color. Be like, okay, let it be yellow. I think yellow or red. Let's use red. I think red will be more visible, right? So yeah. So not to have any controversies with people over which color means what. So jokes aside. So guys, this is what we have. So let's say when I press the button, I want the LED to remain on. That is one way of thinking about this. Or when I press, for as long as I've pressed, right, I want the LED to turn on and off indefinitely without limit, right? Indefinitely without limit. So let's see how we can do that. So that means we've won ourselves a new variable, right, that represents GPIO PB3. So let's call that one. I will come again and say int for integer. LED, let me call it LED pin. This one is on 3. This one is GPIO 3 or PB3. So this is another global variable as well. So do we get the point? So that means I need to set this its pin mode as well. So I'll come and say, instead of button pin, I'll say LED pin. Instead of input, I'll say output. See? That's interesting. So since it's output, I'll first make sure I start when it is off. I'll use the digital write function to start when it's off. So I will say I want the LED pin. So the purpose of having variables is that, think of it this way. If let's say I wanted to change this LED from PB3 to PB4, everywhere I use that GPIO, I'll have to change it everywhere throughout the code. And this is just a simple example, and we are already 20 lines in, 20 lines of code, right? And we are going to get more. Let's say you have hundreds and hundreds of lines of code. You can't keep checking and looking for GPIOs everywhere. That's if you declared them with numbers. You have to declare it with a variable, such that if I want to change sorry, so that if I want to change, I just come here and say 4. You get the point. So, and it changes everywhere else because I'm referencing to it with its variable name. All right. So I'm saying digital write lead pin low. You get the point? I want to start when it is off. That means, remember, the low gives a voltage here that is close to 0 to 0.8. So there isn't enough voltage drop across the LED to turn on, right? So, all right. So now that is what we have. So what is the logic? Remember, guys, we always have the logic. We always have our logic. To implement, we have logic. So which logic should we use? We are saying this is what we want. This is what we want. This is what we want. All right. When the push button is being pressed, right? When the push button is being pressed, when the push button is being pressed, when the push button is being pressed, let the LED flash on and off. Flash on and off indefinitely. And remains, and the LED, let me be specific, and the LED remains off otherwise. Otherwise, and the LED remains off otherwise. You get the point? And the LED remains off otherwise. That means that if you don't press it, it just remains off, like the way we're seeing it here, right? So how do we implement this? We can simply come here inside the loop and start now executing. So that was the preparation, right? So now let's go to the execution. We are going to use what we call a while loop. A while loop. This is how it goes. It goes something like this. We use the keyword while. You see it even changing the color. So, and this is how it works. So while the test, I'm just writing, this is not part of the code. Test condition is true. While the test condition is true, execute this block of code and recheck the condition, right? Again. So let's say whatever we've placed inside the test condition narrows down to a true. It just comes down to a true. Let's say we are comparing two values. X equal to 4. The moment x is equal to 4, they will execute, the while loop will execute this piece of code, and the moment it's done, it comes back and tests. It does not exit the scope of the while. That's the difference it has. That's the major difference it has with the ifs, with the if, else if, and the switch case. Like I said, I may not cover the switch case. I will leave that for you guys, for your own study purposes, for your own research, so that you can relate it to the else if, because it's really close to the else if control structure. So the difference between loops and the other control structures is that the moment the test condition narrows down to a true, we execute the block of code indefinitely. That means we keep on executing this code and coming back. The moment we are done with the last line of code in that block, we come back and test. The moment it narrows down to true, yes, we are back again and execute, then get back. Only and only we will exit when the condition, so we execute this line of code that is outside the while only when the condition came out false. That's it. That is how the while loop operates. Now, in our case, what is the test condition? Let's fill it out slowly. What is our test condition? Our test condition, remember, is detecting a button press. But we said the moment we press, GPI or PB2 goes low. That means let's first create. Now, here is the time where we can use local variable. Int. We can have int or bool. Pin, or can just say button status, right? Button or button read. Oh, button read is going to confuse people. Button status, let me call it button status. It's just a variable and is equal to digital. You can use this function digital read, this function called digital read button pin. So digital read is a function that tells us, or that gives us a value, either high or low. High or low is the same as true or false, right? High can be represented with a true, low can be represented with a false, right? So we are saving that result into a variable called button state. We are saving that into a variable called button state. So now this becomes, so whatever comes out as the button status is what we are testing. So that becomes the test condition. So we come here and say, so our test condition, look at the test condition. While button status is double equal, that's the one that compares. Single equal is an assignment operator. So is this equal to true? Is this equal to true? So if it is equal to true, we should come inside the loop. The moment we test that true, what do we need to do? Remember, we said we need to flash this on and off, right? We just said, that means turning it on, holding a little, turn it off, hold a little, and repeat. So that is digital write, with digital write. It is connected to PB3. It is connected to, the LED is connected to PB3. So digital write, the LED pin, capital high, capital H, capital I, capital G, capital H. So high. Then we have to hold that state for a while. Let it be in that state for a while. So that will be evident by that will be evident from the LED staying on for that long, right? So we come here and say, let's say let it be on for half a second, 500 milliseconds, right? Then I'll copy the whole of this not to repeat. I'll copy the whole of this not to repeat. I'll copy the whole of that not to repeat. So I'll copy the whole of that not to repeat. So it remains high, then it goes low. Then it has to hold that state for a certain amount of time. For ease, let's have the equal amount of time for on and off. So once it's done, it goes back to the test condition and checks. Is the button status true? The moment it's found out true, right? So, but remember guys, let's not use true, let's use low is equal to low. It's easier that way. So we are testing for when. Remember we said it is easier that way because the other way I'd written it would involves flipping the logic. Let's keep it simple. So remember I said when I press, this ground is going to cross all the way, so it's going to have 0 volts. That's a low. So we are testing for a low, right? A low, always 0. You can use the number 0. So for ease, we just use keywords that are easy to read. So while the button state is equal to low, flash the LED, digital right, dead that high, delay for half a second, take it low, delay half a second, then go back to test. If we find it that it's true, it's still low, then we take it high, like that, like that, like that. But the moment I let go of the button, let's have I'm pressing and it is flashing, right? I'm pressing, it's flashing. The moment I let go and they are done with this part, they come to test, it's no longer low, it's false. That means we just have to run this piece of code. Run this piece of code that whatever we will have put here. That's only when we exit the loop. It's like saying you first do this. It's like you're taking an examination. You're not going to play football while playing an examination, while writing an examination, right? You're writing your papers, test or final. You are doing that task first. While its conditions are still there, true, the time is not yet for getting out, right? The time is not yet due, right? For getting out of the examination room. You are going to remain there, do whatever you have to do, write your exam, not until you finish. That's when you pay attention to other things, football, you watch your WhatsApp statuses, whatever. You get the point. You get to do other things in life. You run your day-to-day programs. Only that you were stuck somewhere. Mark the word stuck. You were stuck somewhere in your daily routine, daily program. You're stuck somewhere due to certain conditions, like getting stuck in traffic jam. So only when the traffic jam clears, that's when you move, right? So that's how loops operate. And in embedded systems, we need these loops because there are scenarios whereby the moment something happens, we need to let go of everything else. First focus on that, not until it's completely cleared, not until the conditions are completely cleared. That's when we choose to do other things. So that's how while loop operates. So let's compile and see. Compiling simply means we are putting together all of these instructions and narrowing them down to ones and zeros the microprocessor or controller can understand. So we have no issues. So the sketch constitutes 9% of program space, blah, 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 blah. So what we are going to do So we are going to save. We are going to save. We are going to save it. We are going to save it somewhere. So let me come here. We are going to save it somewhere. We are going to save it somewhere. Let me see documents. All right, it's easier when we save it in documents, right? It's easier when we save it in documents. So let's save it as, let's save this program as while underscore loop lecture 06, lecture 6, right? All right. So it's done saving, right? All right. So after saving it, now let's try to let's do it like this. Let's flash it onto. You can right click, load firmware, whatever. So I just saved a file, then copied the hex, the converted file, the binary file to our microcontroller simulation. So we are going to run the simulation. So that is what we have. So the simulation is now active. It's running. Simulation running, right? So let's press the button and see. Lo and behold, we are seeing a flash. So the LED is flashing indefinitely for as long as I'm holding, guys. I'm holding on to at the moment. So my laptop is touch screen. Let me try using the what? So it does not work that way. So the program doesn't recognize the touches. So this is it. Every time I hold, so I let go, it is still seeing it. It is still seeing it as a flash. What is happening? Why is it still flashing? So you remember what I talked about in one of the, I don't remember which lecture exactly. I remember talking about two types of errors. We have syntax errors. These ones don't even allow you to compile the code. The code will refuse, right? The code will refuse. The code will refuse. You get the point. The code will refuse. So that's let's say you forget to put a termination character at the end of a command. Let's even try compiling and you see what I mean by syntax errors. Let's try it's flagging that a line before it is like it expected. Let me get this out. Expected this before the delay command. It expected a termination character. So that is easy to fix. When we compile again, it compiles. When we compile again, it compiles. So there are no issues. Now, the other kind of error. So let me write it down here. We have syntax errors and we have what we call semantic errors. Semantic errors. So semantic errors are nothing more Semantic errors are nothing more than errors that come out of that come as a result of not having the results you intended to have. In this case, we intended, let me press again. Let me run okay, simulation stopped. Let me run the simulation again. Simulation running, right? So we intend to implement this piece of logic whereby while I press, or as long as I've pressed, it should keep blinking. The moment I let go, it should stop. But in this case, it is not stopping. What do we think is happening? So this is a semantic error. So we need to look for a bug. This is what we call a bug. Errors are called bugs. So now we have a bug. Semantic error is also known as a bug. B-U-G. A bug in the code. Error in the code. It's not doing what we intended to do. The moment I let go, it must stop flashing. Because we said it only executes, the while loop must only execute this piece of code. Must only execute this piece of code only and only when button status goes low. Only when button status goes low. You get the point? So that is what we are having. So let's go through the code line by line. So on the 25th line, we are initializing a local variable called button status, right? Right? As a boolean, right? And we are saying that variable is an assignment of what digital read button pin brings in. And we're like, while button status is equal to low, or let's try saying false. Is equal to false, right? So let's turn on the LED pin, hold for half a second, turn it low, hold for half a second, then come back and check. So let's compile this again. Let's compile. Yeah, now it's done compiling. So I'll come here and reload the firmware to the simulation. Then I'll run the simulation again and see what's happening. So when I press, that's nice, it should keep blinking. Now the issues come in when I let go. When I let go, now here is the problem. Here is the problem. Instead of having button status come from a function that we're calling outside of the loop, let us change this a little. Let's do away with the button status variable. Let's do away with that and do away with that. Let's call the function itself inside the test condition. Directly recompile. I recompile because now I'm not pressing and it's still flashing. So our logic is not coming out right. Oh, okay. So I have to delete this. So a syntax error. It was not. It refused to compile. It refused to compile because I had made syntax. So it's like today I'm all about making errors. So let me recompile again. Let's watch. Guys, the whole course unit is almost programming. So there are no shortcuts to this. There are no shortcuts. No matter how much you want to wiggle your way out of this course unit, it's programming all the way through and through. The remaining sections, what, test, what, Practical lessons, it's just around 20 or 40% at most. So 60 to 80% it's coding. Okay, so now, and that is what you're doing with your projects, right? So let's stop the simulation. Let's reload the firmware and run again. Simulation running. So without pressing, this is what we need to have. Yes, that's nice. Now let me press. Okay, we're having flashes. Let me hold it for a little longer. Definitely it is now a press. It has detected a press. Now let me let go. Ta-da. So I don't think now I am in a position to explain to you what the real problem was, because you will not understand the difference between local variables, global variables, stack and heap. For now, let's not dive deep into that. So every time we want to test a condition, let's slap the entire function into the test condition, right? So that is how it is. So every time I hold, that's what it does. Every time I hold, that's what it does. I let go, it does that. So we can even have another LED. Let's stop the simulation. We can have another LED connected, right? Let me close that one off. Control R. Connect that side of the LED to ground as well. That's nice. Now the other side is going to connect to PB4. You know what this means already. Now let's have that. Copy, paste. I move that around so that I have a copy now, right? So I want a second push button, right? Connected to PB1. Connected to PB1. So I have now two push buttons, right? Like we had in the previous setup. Two LEDs. Now, let's say if I press this one, the one on the far right, I want it to blink. I want it to blink only 5 times. Only 5 times. Now, we can do this with a while loop, and we can do it with another kind of loop known as a for loop. We can even do it with a do while, but let's first focus on the while loop. So here we were blinking indefinitely or flashing the LED continuously. Continuously. So now we want to blink or flash a number of times. Let me call it blink. The second LED 5 times only. 5 times only. So guys, I hope you're now understanding the role of variables and what. So we've added another output and another input to the system, right? We've added another output and another input to a system. So we have to cater for them as well. So nothing new here. We say int. Let me call this button Oh gee, look at the way I'm writing the word button. Button pin 2. Button pin, let me call it right. Button pin R to the right, to mean the one on the far right. It's connected to PB1, right? Is equal to 1. So I'll come here and say int, say lead pin right. The one that corresponds, the one that's going to act in accordance to changes in the right button. So I'm calling it also this one. I'm also calling it this one. This one. I'm also calling it lead pin R. It's connected to 4. That's nice. So we have to make pin modes. Have to make appropriate pin modes. I'm declaring that one as an output. Now button pin R. I can declare that one as input. So we get it. I can declare this one as input. And declare this one as input. This is amazing. So now we've added more hardware. We've added an input and another output. So let's write the other logic. We can say while, remember we write the keyword while, the test condition and the scope. So the test condition is we have to digital read. Copy that condition. It's identical to what we're going to do. So digital read button pin R. The other one, the one I've named button pin R. You get the point? The one I've named button pin R is equal to false or low. I can write 0. 0 is the same as false, low, whatever. You get the point. They all are exactly the same thing. They do the same thing. All right, so what do we need to do? We need to do this for the other LED, right? So instead of lead pin R, we've agreed it's lead pin R. We can even first test this one out. Let's first test this logic. Right, Control R to compile. Let's hope we have no syntax errors and any semantic errors. Here it is saying button pin R was not declared in this scope. Input, saying input. I wrote input, not input. So you see, compilation is the first stage. We must first pass. All right, so done compiling. That was a syntax error. Instead of writing input, I had written input. That is not known. And the only way it can accept it, that's if I declared it as a variable first, and it was neither. So let's reload. Let's reload the firmware and run the simulation again. So let's press this one. So you see, even that one is blinking. When I stop, it should stop. The other one should blink on its own. That's interesting. That's nice. So, but I want to press and only end up with 5 blinks, no more. 5 blinks, no more. I can even press once like that, and it goes 5 times. Here I press once, only goes once. Press once, it goes once. So that is not what we want. We want another kind of logic. Let's have second logic. Let's have the second logic. This is logic 1. This is logic 1. Logic 1. Now let's copy this. Logic 2. We can have logic 2. When the push button, when the R push button is being pressed, let the R LED, the right side LED, flash on and off 5 times only, and the LED remains off otherwise. So that is it. So here now we have to do something interesting. This is how we can do it. We can now create, let's say we are doing this physically. Let's say if someone turns on the lamp, a light in a room, you have to clap your hands 5 times. That means you have to have means of keeping track of the times you clap. So let's call this, we can create another variable, and it's whole number. Every time you're counting 1, 2, 3 times, or number of times an event occurs, we can't have 1.5 times. It's only a discrete number, so it's an integer. So you can call it flash count. You get the point. The flash count. It starts with 0. We don't know how many times we've flashed. We haven't yet flashed any time. So and it's a global variable. So we can come while this is equal to 0, we can do something. Remember, now we are testing 2 conditions. We've pressed the R button, and the number of times we have flashed are not yet equal to 5, but we are starting from 0. So we can have a logical AND. If you remember the operators, the logical operators, AND flash count, not flash time, it's flash count. The variable I've named it flash count, and flash count, hope you can still see, flash count is a variable, is greater or equal to 5. Actually, if it's starting from 0, greater or equal to it is greater or equal to 4. Because if we start from 0, 1, 2, 3, 4, those are 5 times of execution with 0 included. All right, so we have to count for 1 when it is equal. Actually, we can even stop at 4. We don't even need to go for greater. Equal to 4. And flash count. So we have to test for 2 conditions now. And remember, this is an AND operation. An AND operation only narrows down to true when both sides are true. Is it true we've pressed? Let's say we've pressed and it's like, yeah, we've pressed. Then, is it true flash count is equal to 4? Let's say for our case is equal to 0, like the very first time, and it's a global variable. That part is not going to be true. That means the whole of this is not going to be false. You get the point? So, less greater or equal to 4 or less or equal to 4. It should be less. So guys, here the condition should be a less or equal to 4, because the moment I say equal, that means the LED will never flash until count flash is equal to 4. So let's say for the first scenario it is equal to 0. Let's say for the first time is equal to 0. For the first time is equal to 0, flash count. So flash count is 0 is less than 4. That is true. Button has been pressed. That's, let's say we've pressed. That's true. Then we run this. After running it, we only count after running. We must change. So we can say flash count is equal to the current value of flash count plus 1. That's interesting. So every time we count, you get the point. Like, we are done with that part. Every time we flash, we increase or we increment the flash count by 1. As we check, remember the moment we are done with this, we don't exit the while. We come here to check. You get the point. So by the time now, let's say we've reached the 5th time, whereby flash count is equal to 4. Then we flash it for now that will be the 5th time when flash count is equal to 4, because it starts from 0. Now, the moment we increase the value of flash count 2, we increase the value of flash count to 5. You get the point? It will be no longer less nor equal to 4. So this part being false will never allow, even if we keep on pressing. We shouldn't. That's what. So you never know. You shouldn't. We could have made a mistake in the what? In the coding. So we shouldn't get any more flashes. So let me compile this. We are running out of time. Let me compile this. And see. Yeah, we've compiled. Okay, let me stop the simulation. Let me do this. All right. Okay. Let me do that. So simulation running, right? So I press the first one. Okay. Oh, I have to reload the firmware. Then I start running the simulation again. So when I press the one to the left, it flashes indefinitely. Now let's see what happens when I press the right. 2, 3, 4, 5. It should not come back. And guys, I'm holding down onto the button. So I let go. So you see, it should never come back. Because flash count, the last time we updated it was inside the while. It was inside the scope of the while, and it has not been updated anywhere. You get the point? So this is it for the while loop. So in the second part of the 6th lecture, let's look at the for loop and the do while loop. So thank you for being attentive, students. Let's meet in the second part of the 6th lecture.